In addition to performing raster overlay analysis using extraction or map algebra, there are a number of raster overlay tools that we can use to combine weighted rasters into a composite raster. And we commonly use these tools to perform suitability modeling, which is a common scale applied to dissimilar input to create a single composite output. And so the general workflow for creating a suitability model employs the following 5 general steps. 1, standardize geometry. 2, standardize values. 3, weight the criteria. 4, create the index. And 5, identify the locations. So your client has defined the goal, and you've assimilated the suitability criteria required to inform your analysis. In step 1, you standardize the geometry, where you're converting the input suitability criteria into standardized raster data sets with the same cell size. And so, for example, in the diagram on the right, you can see that we've converted elevation to a slope raster, soils to a soil erosion raster, and streams to a stream distance raster, all with the same cell size. In step 2 of the workflow, you're going to standardize your values, where you're going to transform the criteria values to a common scale. That common scale is referred to as a suitability scale, and it could be, for example, 1 to 3, 1 to 10. For example, where 1 is most suitable and 10 is the least suitable. So in this example right here, we use the reclassify tool to reclassify the slope, soil erosion, and stream distance rasters into reclassed and standardized rasters with suitable slope, suitable soils, and suitable distance. If our suitability index is 1 to 10, where 1 is most suitable and 10 is the least suitable, then the greens are scored as 1, and then the yellows maybe as 5, and the reds as 10. In step 3, you weight the criteria. Weighting allows certain criteria to have more impact than other criteria. In this particular diagram, they're all weighted the exact same, times 1. But if I felt like slope was more important, then I could multiply it by 3, for example, and it would have 3 times the impact than the soils and the suitable distance would. In step 4, you're ready to combine the standardized and weighted criteria into a single composite suitability index. And there are 2 general approaches for doing this: weighted sum and weighted overlay. In weighted sum, criteria are combined by summing the coincident cell values. Criteria A plus criteria B plus criteria C equals the sum index value. Or you can use weighted overlay by multiplying by a fraction of 1, i.e. the percentage, and then summing the coincident cell values. Criteria A times 0.33 plus criteria B times 0.33 plus criteria C times 0.34 equals the percent index. Now, either approach will produce visually the same raster, but if you look at the underlying values, with the sum index, the max value is going to be 3 times what your maximum value in your suitability index is. So if it's 10, the max value would be 30. But with weighted overlay, the max value will be the top end of whatever your suitability index is. So in this case, 10. And last, in step 5, you identify the location or locations. So you use the suitability index to identify the most suitable location or locations for your particular use. Now let's take a closer look at these raster overlay tools. So overlay tools weight input rasters by multiplier percent and total the coincident cells into a composite raster. We use the weighted sum geoprocessing tool to weight input rasters by multiplier and total the coincident cells. The input rasters can be integer or floating point, that means whole number or decimal, and must be reclassified to the same value range before using the tool. The rasters are multiplied by the weight and summed. If you look at the example on the right, you can see I've got an input raster 1, an input raster 2, and my output composite index. And the math works like this. For input raster 1, the upper left-hand cell is multiplied by the weight. So it's input raster 1, 0.75 weight times 2.2 plus input raster 2 weight, 0.25 times 3 equals the output cell value of 2.4. Now the output raster value range can be greater than the inputs. In this example, it's not, and that's because my weights are less than 1, 0.75 and 0.25. But if my weights were greater than 1, for example, input raster 1 was weighted with a 2 and input raster 2 was weighted with a 1, then my output might be greater than the value range of my input. So in this example right here, if the input raster 1 weight is 2 times 2.2 plus the input raster 2 of 1 times 3 would equal 7.4. And 7.4 is greater than the values that range from 1 to 3 in the input rasters. Now, this is an important point because we use the weighted overlay geoprocessing tool to weight input rasters by percent and total coincidence cells. And if you go all the way to the last bullet point, you can see that the output raster value range is equal to the inputs. It can't exceed. And so the input rasters for the weighted overlay tool must be an integer and can be reclassified before or in the tool. And this also differs from the weighted sum tool, where input rasters can be integer or floating point and must be reclassed before using the tool. So the weighted overlay tool needs to use whole numbers, but you can reclassify in the tool. The rasters are then proportioned by weight and summed in the output raster. And in this example, if you look at the upper left-hand corner, you can see how the math works out, which is input raster 1, weight 0.75 times 2, plus input raster 2, weight 0.25 times 3, equals 2.25. And of course, we have to round that because the output must be an integer raster. So the resulting cell is 2 in the output raster. So for me, which tool I use really depends on the analysis I'm running and whether my input rasters include decimal or floating point rasters, because that's going to be weighted sum, or maybe I want my composite raster to have the same value range as my input rasters. In that case, I'm going to use weighted overlay.